Thank you, Mr. Chairman. So I will discuss about the characterization of the superconducting joints for the colloidal field coils of ether. And I will discuss about some introduction about ether for those who are not familiar. And then I will talk about the DC resistance and AC loss tests of these joints, and something about the modeling with a distributed parameter electric circuit and with the 3D frame model. And then I will come to some conclusions. The fusion reaction takes place at temperatures of 100 or 200 million Kelvin, which requires some confinement. In a tokamak, the confinement is obtained by combining a toroidal field, which is generated by these so-called toroidal field coils, and a colloidal field in this direction, which is generated by the current flowing in the plasma. So when you combine the toroidal field and the colloidal field, you get this helix-like field, and the particles, charged particles, will rotate around these field lines, and then they will be confined in the machine, in the torus. So the ITER project, International Thermonuclear Experimental Reactor Project, is as a purpose to demonstrate the feasibility of energy production from controlled thermonuclear fusion. It was started by Soviet Union, United States, European Union, and Japan, and then subsequently joined by China, Korea, South Korea, and India. And the 7 ITER parties now represent more than half of the world population and 2/3 of the gross national product. So essentially, the ITER project aims at producing 500 megawatts power with a Q factor. What we call Q is the ratio of the power exiting from the system with respect to the power entering the system, which is 10. So this will be 10 times the power entering the system. And there are 18 toroidal field coils, which are these around the torus to generate the toroidal field that we were talking about. The central module, which is essentially the primary of a transformer, of which the plasma is the secondary, so varying the current in this module will induce the current in the plasma, which in turn generates the colloidal field we have seen before. And then we have these colloidal field coils, which are very large magnets up to 25 meters diameter, and which essentially are used to, for the plasma stability. And then there are some also correction coils to improve the quality of the field generated. You can see that some magnets, like the TF magnets and the CS coils, need to go to up to 12 Tesla or 13 Tesla, and therefore they require niobium-13 cable and conduit conductors, whereas the PF coils, these that we will focus today more, they only need to reach about 6 Tesla, and therefore they are made with niobium titanium cable and conduit conductors. Essentially the coils are wound from cable and conduit conductors. So there are superconducting strands mixed with pure copper strands, like here you have 2 superconducting strands and 1 copper, and then they are assembled in multi-stage rope tie cables. So you take 3 triplets and then times 4, and you get the cable, and then you introduce it inside the stainless steel jacket, this outer part, which is used essentially to contain the flux of supercritical helium that flows inside these cable. The cable we are looking at is the PF cable, which is the one shown here. So now something about the testing of the joints between the PF conductors. You can see that the coils in the ITER magnet system, they have hundreds of joints, and they operate in magnetic field up to 4 Tesla, field derivatives 0.5 Tesla per second, currents up to 70 kiloamps. And you need to test them periodically during production to control the quality, the reproducibility of the electrical performance. So the design is based on the so-called twin box configuration, assembled in shaking hands or praying hands concept. Essentially, you can see here that these are the 2 superconducting cables with all the wires. And then you have these 2 soles of copper, a shim inside of copper to let's say, make it easier from the tolerance standpoint, and then the other sole. The current will have to flow along the joint, this is the joint length, from one cable to the other through the copper. So of course there will be some resistance, which is the resistance of this part of copper. Then the whole joint is cooled down through helium pipes that essentially allows the cooling of the joint. How do the essentially, we can see that there is a stainless steel box outside, and this stainless steel box presses practically the cable over the copper sole. So this is pressed, the cable is pressed to the copper, and this reduces the joint electrical resistance. So you can see here that with the compaction, the cable is not circular anymore. It takes this sort of oval shape. How is it tested? We have this facility called Sultan, which is in the Swiss Plasma Center in Villingen in Switzerland. The samples are essentially cables which are about 3.6 meters long. And here at the bottom, you have a high field zone. The field, the DC field, is generated by these split solenoids, 3 pairs of split solenoids, one inside the other. And you can, with this, set the DC field. And here there will be essentially the joint. How is the joint instrumented? So you will have the DC field I was talking about in this direction. And then you will have the possibility to also have an AC field generated by these coils, which are essentially generating a pulsed field with some sinusoidal shape, which is typically of 0.2 Tesla. So at the joint, here are the 2 cables, and this is the copper. You will see that this is the distribution of the AC field, let's say at a given instant, of 0.2 Tesla here, and then it becomes lower field at the extremities of the joint. So this is the joint, and these are essentially the AC field coils. The DC resistance is measured with different background field, and also with different orientation of the transport current, because since the DC field is fixed, when you change the orientation from plus to minus, so the current flows from here to up there, or from minus to plus, but the DC field has the same orientation, so in one case the 2 cables tend to detach from each other to separate the Lorentz force. In the other case, they are pressed essentially towards each other, and so this could, in principle, generate some differences. So the resistance of the joint is measured by 2 sets of sensors. First set, you take the resistance, the voltage from here to here. This is what we call the near section. So the current flows inside, exits from the joint, and I take the voltage from here to here. We call it the near section. Otherwise, the far section is, let's say, 450 millimeters away, and you take the voltage from here to here. So in between, you have the joint, plus a part of superconducting cable. In principle, this should not change the measurement because this is superconducting. But we will see that there is a different result between the far section and the near section. Although here we should not have any resistance. All the resistance should be located here where the copper is. So if you look at the difference between the far and the near sensors, you will see that you have 2.5 nano in the near sensors and 4.2, a significant 4.3 at the far sensors, which is also in agreement with some calorimetric estimation that you can do based on the energy enthalpy variation of the helium flowing inside the joint. So you can see that this is pretty, it increases not so much with the field. Here you can see the increasing values with the field, and the green, the orange is 5 Tesla, yellow is 3 Tesla, and green is 0 Tesla. So there is some slight increase. The good thing is that apart from this badly soldered joint, which was above the criterion of acceptance of ITER, which is 5 nano, all the others during the qualification phase to accept the manufacturers and during the production phase, they all were below the acceptance criterion. So this is the main result of this phase of control of the quality of the joint. This is a very important result. So here we have the effect of the current orientation, so with plus or minus 55 kiloamps, but there is not such an important effect. So this is practically insensitive to the orientation. And then here you can see the impact of the cyclic loading. So essentially, you go from the zero current to 55, you go back to 0, 55 again, like that. You did 100 times, 500 times, 1,000 times, and you can see in some cases nothing changes, like with the Pf conductors, and in some other cases, especially in the first 100 cycles, you have some increase of resistance, which then tends to stabilize a little bit more, but in any case, it's below the 5 nanohms, so this is not a concern. If you look at the AC losses in the joints, we talked about this plus minus 0.2 Tesla, and so, for instance, you can look at this curve. These are various joints. This is the AC loss per cycle versus the frequency of the applied sinusoidal field. And you can notice that, for instance, with plus minus 0.2 Tesla, this red curve, you have these values, and about 1/4 if you have plus minus 0.1 Tesla. Which is in agreement essentially with calculations, because this is essentially from the theory, it goes with the square of the delta B that you have. If you take the yellow curve, it is interesting to note that you have an impact of the field. The DC field is when you have only 1 Tesla, you have this curve. It goes down if you have a DC field of 3 Tesla. So you have the AC field the same, but the impact of the DC field is what you can see here. Okay, so next, another aspect is, does the transport current impact the losses? In most cases, it does not. So you can see the dotted is with transport current and the solid is without transport current. There's not so much difference. Only in one case, this orange sample here called the PFJU9, you have some significant difference. But this was not according to specifications. So this joint had essentially a copper in the saddle that was made of high purity copper, instead of a copper with low triple R that is normally adopted with triple R around 6, exactly to limit the AC losses. The copper purity is not that great because we need to limit the AC losses. So now I will come to some modeling of these results performed with a model that we call TELMA, in which essentially this model represents the superconducting cable through connected through joints and terminations to a power supply. This is a power supply. You have some joints and terminations. The geometry can be of any type, like a cable in conduit conductor, like you can see here for this coil, or a Rutherford cable. And the cable is modeled with the distributed parameter circuit, where you have some cable elements that can be either individual strands or subcables, so groups of strands. Essentially, in the model of the joint, what we did is to represent the copper soles and the shim, so this part of copper, with some what we call the joint elements, in this case 234 joint elements, and whereas we represent subcables of the cable, in this case with 30 cable elements, in this case with 102 cable elements. For instance, 30 cable elements correspond to taking the last 2 stages. So this is 4 stages, 4 times practically the stage 2. So this is 1, 2, 3, 4 times, plus 1 cable core made of only copper, which is the one you can see here in red, and the other 4 correspond to the group of strands. So each of these represent a bundle of strands, which is what you can see here, and each is a bundle. And otherwise, you can have a model which includes all the 102 cable elements at the 3rd stage, essentially. So each is a subcable. Practically, each of these represent a subcable with a certain number of strands. Now, when you look at the model parameters, we have a conductance per unit surface between the subcables belonging to different petals, like the petal is the last stage of cabling twist pitch, and this is a conductance between, let's say, the green and the blue, which belong to a different petal, or in the same petal, this is the conductance that we have, or with the copper. So these are the parameters of the model, because also between the superconducting subcables and the copper, you will have some conductance, and we can, vary these parameters. Essentially, there's some problem there, sorry. We also have tried to check the discretization of the copper saddle, And we have noticed that DC resistance goes from 3.86 nanom to 4.1 nanom, and 4.11 if we have 444 elements in the joint. And we selected this one because the change from 4.1 to 4.11 is not large, but this essentially allows us to have a better, let's say, a faster calculation of the AC losses. Also, as I said, we have compared the model which has 30 cable elements with 102 cable elements. If you keep the same values of the parameters, so the conductances between the various subcables, you get this type of difference. You should recall that in the two cases, the contact surfaces are different. So in principle, one could change the parameters. This is just what happens if you keep the same conductances between the subcables in this model and this model, and you get this kind of difference between the two. But for us, the final model essentially is based on the 234 elements in the joint here and the 30 elements in the essentially in the cable, because this is the one where we have a fast calculation or not too long computation time. And I think it is interesting to note what happens in the calculation if you take only a perfectly resistive joint, so only the copper part of the joint without the niobium tie cable. This is what the result would like in terms of loss versus frequencies. This is joules per cycle, And it is interesting to note that if you add the cable, the calculations show you something that is much more similar to the experimental results. This is all calculation. And what is this due to? It is due to the shielding effect of the currents flowing in the cables with respect to the copper which is in between. So these currents will shield the copper inside and will change the shape of the curve. So this is what the model tells us, that this variation is due to the shielding effect, which is also dependent on the parameters. So if we change the conductance between, for instance, subcables belonging to different petals, you can see that you can enhance the screening effect because the currents between subcable in the cable increase, and so you increase the screening effect, and the losses, practically the effect is that they decrease at high frequencies because you have higher screening of the copper. Otherwise, it would go up like this, and then it increases at low frequencies. So this is what is the impact of this particular parameter. So essentially, if you compare to experimental data, we have kind of a good agreement between the measured and the calculation that we have, let's say, with the parameters that we are using. And you can see that in this case, also the calculated and measured joint resistance is around 4.3 nanom, which becomes our reference. This is the value given by the FAR sensors. And it's important, and I will come back to this in a moment. Okay, so this is the result from the model. I will also show you another model which is based on 3D FEM that was implemented in ANSYS Maxwell 3D. Essentially, here you can see that you can put everything in the model, so the stainless steel and the copper and of course the niobium tie cables. Here we have also the AC coils that generate the field. So here we have a very simplified approach to model the niobium tie cable, practically a homogeneous anisotropic material. So a very large conductivity along the z-axis and a smaller conductivity in the plane orthogonal to the z-axis, so x and y axis. So it's a simplified model, but still helpful to understand what happens. And especially what you can do here, you can calculate the DC resistance with this model. For instance, imposing that you have a certain voltage on this side and either 1 volt or 100 microvolts and 0 on the other. And here you can see the distribution of the voltage from, in this case, from 1 to 0, and the distribution of the current flowing along the cable, which of course is maximum in the beginning, and then it reduces because it has to flow, let's say, in the transverse direction to reach the other cable. What is interesting is that practically the measurement I have shown you before, the near voltage steps measure 2.5 nanom and the far voltage steps 4.3. But this model, if you put to 0 the resistivity of the niobium tie cable, practically with a very, very large conductivity, you can see that the impact of the copper only to cross the copper, you would have a resistance of 3.57 nanoms, so higher than the 2.5 measured by the near voltage steps. So the model tells us that the far voltage steps results look more reliable because 4.3 is greater than 3.57, which is only the contribution of the copper, but you have to add the fact that the current must flow from the strand to the strand, the other strands, and then to the copper. And so this seems more reliable. And now ITER is using this measurement from the far voltage steps for the assessment of the DC joint resistance. And then for the AC loss computation, even though the model of the non-magnetite cable is very simplified, you can still see that it is, however, possible to more or less reproduce qualitatively the features of the losses, AC losses inside the joint, and to improve a little bit the let's say the fitting. We also added a thin layer, a resistive layer, to practically simulate the resistance between the strands of the cable and the copper of the sole. Okay, so I will come to my conclusions. Practically I can say that the PF joints satisfy the 5 nano criterion at 5 Tesla, so this is a successful result. The DC resistance is practically insensitive to current orientation, and it slightly increases with electromagnetic cyclic loading. This is what we get from the experiments. What do we get from practically from the modeling is that we have two numerical models developed. They can reproduce correctly the DC resistance measurement, and they represent useful tools to compute losses under operating conditions which differs from those in the Sultan facility, because there you have a fixed field orientation, amplitude, time evolution. Instead, with these models, we can practically simulate all the various situations of the joints inside the machine. And the next step will be to apply the models to calculate the losses in a typical plasma scenario where you will have 15 megaamp in the plasma. And so this model can practically simulate situations that cannot be obtained in the Sultan facility because of the different field orientations and so on. So thank you very much for your kind attention.
Thank you very much about your presentation. I wonder, there are two superconducting wire, and you joined through the like a superconducting part. So I wonder, what about the joint distance and also the thickness between two superconducting wire? Is there any? So you use the model. Did you calculate the optimum length, joint length?
Thank you. It's a good question. Actually, the joint length normally is taken so as to have the length of the last stage twist pitch of the cable. So which is around 420, 450 millimeters. This is in a way that most probably, not all of them, the strands will at least be in a position that they will touch the copper more or less directly. This will not really happen for all of them, but so that they are as much as possible in contact with the copper. So this is important. It's considered as important to have this kind of length over which most strands, essentially they have the possibility to touch the sole. It will not happen for all the strands, but there have been tomography analysis, and more or less you have pretty good contact for a significant percentage of the strands. So yeah, this is important. The length of the joint is something that is relevant.
Yeah. Another question. I want. It's mechanical contact, right?
Well,
not soldering or
no, you have some superficial solder as well. Okay, and you can with this kind of tomography, they found out that 50% of the strands are well soldered at the contact surface. 50% of the strands are well soldered. So there is a solder, but not filling the whole area, only between the strands and the copper sole. Okay, there is some solder.
And also press is there is a maximum critical press value to for example, if you apply the press more than a specific value, so the resistivity of the copper plate and also
Yes,
can be changeable.
Yes, there is essentially the pressure is given by this stainless steel box on one hand, but also by the Lorentz force in the case that the current is in such a way that the cables are pressed together. So of course you have some limits, but the idea is that with a direct or reverse orientation, this did not change the results so much. So it did not affect so much as we thought the final DC resistance. It could affect more. Okay.
So in this attachment, current measurement used as a torque meter of screws.
I didn't get this.
Yeah, I mean to
screw
value can be estimated by the measurement.
I don't know if this was done. I don't think it was done actually. No, but you can calculate what is the situation. I think. Yeah.
Have you measured the influence of the current cycles?
Yes, it was.
You also measured the temperature cycles.
Yes, there was a case in which some temperature cycles were performed. Not in all joints, and not as many, like 1,000 electromagnetic cycles, but a few, like maybe 4 or 5 thermal cycles were performed. And this did not affect the DC resistance.
Thank you for the talk. What is the reason for choosing 5 nano ohms as a criterion for 5 Tesla? Would it be 10 nano ohms for 10 Tesla, or there's any merit in choosing this number, or it's just an ordinary usage?
This comes from the thermal hydraulic requirements of the cryogenic system, because of course 5 nano will give you some Ri square, so some power entering in the cryogenic system that you have to take out. And so these are criteria that come from the thermohydraulic simulations in which you have limits to the power entering the helium. So you need this kind of limitations, and criteria are set by the requirements of the cryogenic system.
So if your cooling power were higher, then this number would be a little bit bigger. Is this right?
Yes, it's correct, yes.
Okay. Have you tried different joints or measuring or studying, or have you only tried just one?
No, there was in the pre-qualification phase, there were different types of joints, different attempts, and the type of copper was changed to reduce the triple R. So it's not a very high purity copper. It has a triple R 6, this one. It's not very high purity, because you could stay below the DC resistance in any case criterion, but without an excess of AC losses. So it was reduced in purpose. The quality of the copper was reduced in purpose. So it was changed. And this was done. It was a long work of done in the pre-qualification phase.
Thank you.